Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. And we're fully live today, so that's pretty exciting. And I'm really fired up today because I get to talk about a product that I really like. I know I'm fired up most weeks, but I'm extra fired up this week because I get to talk about OCS I/O. OCS I/O is the new I/O family from Horner that you can add to just about any Horner controller in any application. You can use it as your primary I/O system. You can use it to supplement the I/O that's built into the OCS already. You can install it in the same cabinet as the OCS. You can install it up to 500 meters away. It's just super flexible. It's just a very cool product. Now, we've had a couple of sessions on OCS I/O before, but here's our specific topic for today. The new OCS I/O base with its built-in I/O, including flexible inputs. Now, most industrial I/O you see out there these days is modular, and OCS I/O is modular as well. You start with what we call the I/O base. Now, some of our competitors have I/O systems where sometimes they call it an I/O base, sometimes they call it a bus interface unit or a network interface unit. It all depends on the product line. Now, with OCS I/O, we call it an I/O base. Now, with most industrial I/O out there, the whole purpose of the I/O base is to provide as the interface or the connection between the I/O family or the I/O system and the controller. And that's true with OCS I/O as well with our CNX I/O base. It connects via CsCAN to your OCS. Now, one thing that we do a little differently, however, is we also include some additional built-in I/O in the base, which is something our competitors pretty much don't do. So when you get an I/O base for the OCS I/O, you get not only the base and the ability to add additional modules to fill out your I/O system, but you also get 6 built-in flexible inputs or flexible I/O points that you can use in your system. And in some cases, that's all the I/O you may need to fill out your application, especially if you're using a micro OCS. Okay, so that's our topic for today. Let's go ahead and break it down. Okay, we're going to do a quick review of OCS I/O, and then we're going to start focusing right in on that built-in I/O. Through those 6 built-in I/O points, we've got flexible inputs, DC outputs, universal analog inputs, and analog outputs, all different types. Very cool. We're going to talk, of course, about I/O wiring a little bit and Cscape configuration, and we'll have plenty of demonstrations. So let's start with our quick review. OCS I/O, as I mentioned in the opening, it starts with the CNX I/O base. Every OCS I/O system requires a base. What does the base do? Well, it provides that interface between the OCS I/O and the OCS via the CsCAN network. Now, don't be fooled by the connectors. They're RJ45, but they are using CsCAN from a protocol standpoint. It's just by using RJ45 style connectors, and it allows you to use Ethernet style patch cables, which makes wiring that much easier. And remember that I/O base includes 6 I/O points of its own built right into the base. Okay, now something else you need when you start an OCS I/O system is you need a backplane connector assembly. Now, these days, it's available when you purchase your CNX base. At that point, you can specify whether you want a 4-position backplane assembly or an 8-position backplane assembly, and it's no extra cost when you order your base. Now, at some point in 2023, we're going to include a single I/O connector, or backplane connector, I should say, in the box with either your I/O module or your base so that you can do the assembly in the field. But because of a little bit of an issue with the part from our vendor, we don't make this part in-house. It's a little difficult to assemble it, so therefore, at least for now, when you order your base, you can specify either a 4-position or 8-position backplane connector assembly. Now, once you've got your base and you've got your backplane connector assembly, then it's just a matter of filling it out with up to 7 additional I/O modules that meet your requirements for your application. And you can see on the screen there, we've got a whole variety of different options, and it really doesn't matter what combination of 7 modules you add to your CNX I/O base, the CNX can handle it without any problem. Now let's start talking about that built-in I/O. That's really the focus of our topic for today. And again, we've got a total of 6 I/O to review. We've got 2 that we're calling flexible inputs, 2 that are DC outputs, 1 universal analog in, and 1 analog output. And we're going to go into a lot more details than that. And they're all wired to the removable terminal blocks that are located at the bottom of the CNX base, the same point at which you apply your DC power to power the system. Okay, let's start with those 2 flexible inputs. Why are they flexible? Well, they're flexible because they can be used as either digital or analog inputs. That's pretty flexible. Also, if you're using them as a digital input, the input voltage that's used to turn on when the switch or the photo eye or what have you switches, that is also configurable. So maybe you're using 24 volts, maybe 12 volts, maybe 5 volts. Heck, you can even do something custom. We'll talk about that as well. Also, if you're using those flexible inputs in analog input mode, you've got the ability to configure them between different signal types. That's also very cool. And with those 2 flexible inputs, they're independently configurable. So one could be used for analog, one for voltage, or both for analog, both for voltage, depending on what you're looking for. Now let's talk about using a flexible input as a digital input. So you've got a variety of things that you can configure. First of all, you can configure, do you want this to be a syncing input or a sourcing input? More commonly known as positive logic inputs or negative logic inputs. What is the voltage range you're looking for? Is this a 24 volt input? Is it a 12 volt input? Is it even a 5 volt input? It can be pretty hard to find 5 volt inputs these days on I/O systems, and with the flexible inputs, we definitely support that. And if you decide instead of picking a standard range, you pick a custom range instead, you can configure custom on and off threshold points for that digital input. Now let's talk about using a flexible input as an analog input. You can select between voltage mode or current mode. You can select your scaling. Do you want the full 0 to 32,000 scaling range, or do you want something narrower that might be a little easier for you to scale? Now keep in mind, these flexible inputs are 12-bit analog inputs. That's pretty darn good. And so you can choose an appropriate range depending on how you'd like to do your scaling. Now, another thing that's very cool that adds to the flexibility of these inputs is you can actually change their configuration on the fly. In other words, you can change how you've got those inputs configured as either digital or analog and what the range is, etc., etc. You don't have to hard code that into CsCAP. You can actually assign variables or registers to that function, and you can do it in the field. So, for instance, you could build your own maintenance screen where you changed the configuration of those flexible inputs. In some cases, that might be advantageous. You might have multiple applications where sometimes you want to use a voltage sensor, sometimes you might want to use a current sensor, that sort of thing. So it can definitely be advantageous. When you're talking about the configuration words themselves, on that previous screen, what I showed was the configuration details for using a flexible input in analog mode. On this screen, we're showing how you can use those flexible inputs in digital mode and how that changes the values that you put into your registers or your variables at runtime. Okay, now let's go ahead and demonstrate how we can configure and use those flexible inputs. So the first thing I'm going to do is I'm going to switch over to CsCAP here, and I'm going to go into the hardware configuration area of CsCAP. Now there's a couple different ways I can access that. I can go to Controller, Hardware Config, or I can, if I have it on my desktop, I can also select this I/O config or hardware config icon. Now from the main page, I'm going to select the CsCAN I tab. In my case, I'm using a XL7 for this demonstration. It has 2 CAN ports, and my OCS I/O is connected to CsCAN I in my example. Now, because we're just talking about the I/O in the base today, I've only got the CNX base. I don't have any expansion I/O at all. Let's go ahead and double click on this CNX base. All right, and then it pulls up the details for my configuration, where my digital inputs and outputs start from a addressing scheme standpoint. Now I'm using variable-based advanced ladders. That's why you see these arrays here. If you were using register-based advanced ladder, then you would see direct memory addresses here like I33 and Q33, AI33 and AQ33. But I'm using variable-based advanced ladder, so I'm using the built-in arrays. I've also assigned a status variable, which happens to be 15 consecutive words. And we'll talk about that a little bit more later. But most of our configuration for the built-in I/O is handled by this onboard I/O tab. So let's go there now and take a look. Now, so far, we've really just talked about the flexible inputs, and those are handled here in the center part of our configuration dialog. So let's take a look at this here. Okay, so for each channel, we need to click this checkbox to enable the channel. And in my demo here, I went ahead and hard-coded both channels. And I've configured channel 1 as a digital input, but instead of selecting, 12 volt or 24 volt or 5 volts, I went ahead and configured a custom voltage range where my on threshold is 14 volts and my off threshold is 6. Now, if I would have selected 12 volts or 24 volts or 5 volts, I wouldn't have had to fill in the details for the on and off threshold. For my second flexible input, I've configured it as an analog input for 0 to 10 volts, and I've selected a data range of 0 to 32,000. So that's how my scaling is going to work. So at a value of 0 volts coming in, I'll have a digital value of 0. For a full scale value of 10 volts coming in, I'll have 32,000. Okay, so that's how I've got the configuration done for the flexible inputs. All right, let's head to the bench and take a look. So I built this screen here for demo purposes, and you can see I've got 2 indicators for my 2 flexible inputs if they're used in digital mode. And then I have 2 analog indicators that I use for using the flexible inputs in analog mode. Now, you may have seen my input kind of jumping around a bit there. That's because my source wasn't powered up, so everything was kind of floating there. But let's start with our first flexible input, which we have configured as a digital. And if you remember, we had it configured, I believe, for an on threshold of 14 volts and an off threshold of 6 volts. So let's go ahead and pull up my variable voltage source here, and I'm going to gradually bring up the voltage. And when we get up to about 14 volts, we should see that input turn on. Sure enough, it did. Okay, and it stays on. And then if I get down below 6 volts, which I'm not there yet, we should see that input turn off, and it did. Sure enough, there we go. Okay, so that's the first flexible input. Again, using it in digital mode, and in this case, an actual custom threshold area as well. Okay, now let's take a look at this second flexible input, which I have configured for analog mode in 0 to 10 volts. Now I have 0 volts on my sensor or my simulator here, and I should be pretty close to 0, and I'm at just about 5 counts. And remember, we've got 12-bit resolution here, so that's pretty close to 0, obviously. If I have a 5-volt signal, I should be pretty close to mid-range at 16,000. Yep, I am within just a few counts there. If I go up to 7.5 volts, I should be up around 24,000 counts. Yep. And if I go full scale, I should be up pretty close to full scale as well, and I am. Okay, so that went as planned. So again, I configured my first flexible input as a digital with custom thresholds, and my second one as an analog. All right, let's head back and continue on. Next, we're going to talk about our one universal analog input that we have. So with the 2 flexible inputs, we can use those in analog mode if we want, but we have a dedicated analog input also available. And it's universal because it supports a wide variety of sensors, not just voltage and current modes, but temperature sensors like thermocouples and RTDs as well. Also, this universal analog input is 16-bit resolution. That's really good. That's very high resolution. Outstanding. And in addition to being able to set various scaling ranges, 0 to 32,000, etc., if we're using it with a temperature sensor like a thermocouple or RTD, we also have the ability to configure the input range. In addition to that, we have digital filtering, and we also have some optional alarm handling that I'll talk about. Now let's talk about using a universal analog input with a thermocouple. All right, so let's say we've got a thermocouple sensor. We want to connect that to our universal analog input. How do we do that configuration? Well, we need to configure our thermocouple type. We need to select whether we want Celsius or Fahrenheit as the scaling on that guy. And we also need to note that the value will be reported through the analog input register in 10th degree increments. So if I'm in degrees Celsius mode and I've got 100 degrees Celsius that my temperature sensor is reading, then I would get a value of 1,000 because my reading is in 10th degree increments. Okay, so that is using with the thermocouple. If I use my analog input with an RTD instead, I can choose between PT100 or PT1000 sensors. And again, I can select between Celsius or Fahrenheit, and my values are reported in 10th degree increments. For voltage or milliamp range, I have my choice between 0 to 10 volts, 4 to 20 milliamps, or 0 to 20 milliamps. And I have a choice between a variety of different scaling settings, 0 to 1,000, 0 to 4,000, 0 to 32,000, etc. Now, remember, this is a 16-bit input. So if I want to optimize or maximize my resolution, I'm going to be better off selecting 0 to 32,000 as my scaling. That'll be the widest range available. Also, what's the advantage with going to 4 to 20 milliamps versus 0 to 20 milliamps? Because they'll both work, right? Well, if I choose 4 to 20 milliamps, then my minimum of 4 milliamps will have a value of 0, and my 20 milliamp reading will give me a value of 32,000. If I go with 0 to 20 milliamps, well, then I've got 0 milliamps, I'll have 0 counts. At 20 milliamps, I have 32,000 counts. So again, I have my highest resolution with a 4 to 20 milliamp setting. Once again, just like with the flexible inputs, you can actually change your sensor type as well as your scaling on the fly. Again, big advantage, especially if you've got a machine where sometimes you use RTDs, sometimes thermocouples, or maybe you always use thermocouples, but the type can vary from application to application. Well, now you can set up your own configuration screen on the OCS, maybe protected by a password, and now all that configuration of sensor type can be done in the field without firing up CsCAN. Big advantage for sure. Another thing that we're offering with our universal analog input is it has a built-in alarm handler. Okay, so what is that? Well, if you choose to take advantage of the built-in alarm handler, you're going to assign 4 consecutive registers if you're using register-based advanced ladder, or an integer array with a length of 4 to be able to assign in the field 4 different alarm levels: low, 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 high, and high, high. And you can see the status of those alarm conditions by monitoring 3 bits that are pre-mapped to the 3rd word of the status register. So that's how you can access that from your program. So you can tell by monitoring those 3 bits if you have an alarm condition and which one it is. Do you have a high high? Do you have a low, etc., etc.? So having the built-in alarm handler can also be pretty darn convenient. Now let's go ahead and demonstrate the universal analog inputs. And to do that, I'm going to head back to CsCAN. I'm still on my hardware configuration screen in the main area here. And then at the top, this is where we configure our universal analog input. Now, if you remember correctly, on my flexible inputs, I went ahead and hard-coded those in CsCAN. But for my universal analog in, I went ahead and assigned variables to everything. And you could do the same thing with 4 consecutive registers if you're using register-based ladder. For my configuration register, I've created a variable called config_UAI, and it is an array of 3 words, starting at 0, as all arrays do. And then I've taken advantage of the optional built-in alarm handler. I've assigned another integer array, this time with a length of 4, for my 4 different alarm levels: low, 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 high, and high, high. And that's my configuration. So let's head to the bench and let's take a look here. For my universal analog in, because I have the capability of configuring this in the field, I went ahead and set up a configure universal analog input screen here. It's not populated with a lot of stuff here, but it does the job. By using text tables in my case, I can go ahead and I can select between the different sensor types that I would like to use, or I might use in my application. And I'm going to go ahead and stick with 0 to 10 volts here. I can also play around with the scaling a bit. Now this is a 16-bit analog input, so I'm probably better off sticking with 0 to 32,000, but I don't have to. I could go ahead and change to another range here. Let's say I could go 0 to 1,000. I'm losing resolution, but I have that option. And I've got my filtering set. Here's my universal analog input. Now, in order for that to read, I've got to move my wire here from my flexible input over to my universal analog input. And there we go. And as you can see, at full 10 volts, I've got a value near 1,000 because I chose 0 to 1,000 as my scale. If I change to 5 volts, I'll go down around 500. If I go 2 volts, I should be around 200. So there you go. The universal analog in, piece of cake there. To configure that, it can be really useful to have the capability of changing to different sensor types on the fly, as well as changing ranges on the fly. So let me go ahead and change this back up to 0 to 32,000 and recover some of that resolution. Okay, and now you can see that I'm have a significantly higher value because I have more resolution. When I go to 10 volts, I've got nearly my full scale of 32,000. Okay, that's what I wanted to show you there. All right, let's head back to our slides and let's finish up with a couple more types of I/O built into the base. The next one is 2 DC digital outputs. Now, these are solid state outputs, just standard outputs on off, of course. But one of the things that's a little bit special about these is they're pretty beefy. They can handle up to 2 amps DC per point. That's higher than your typical DC outputs in most industrial applications. In most industrial applications, either half amp, which is what Horner outputs are more commonly, or they might be even, 50 milliamp or something like that. But in this case, they're a full 2 amp positive logic outputs, and you can configure them, although it's pretty rare, you can configure them to hold their last state if you choose. But most of the time, you're going to want those outputs to turn off if necessary. For instance, if it loses communication with the OCS, for instance. Now, in addition to those 2 digital outputs, there's also a single analog output. Again, very convenient. Now, the analog output is 12-bit in resolution, and you can configure it for either milliamp mode or voltage mode. In milliamp mode, it's either 4 to 20 milliamps or 0 to 20 milliamps, and in voltage mode, it's 0 to 10 volts. So what do you need to configure there? Well, like you would expect, you got to configure your range, or the output type, I should say, and you need to configure your range. And you have the ability, again, it's a rare case, to have the value held when the OCS controller goes away, or you can have it go to minimum, which is the typical in most applications. Just like the other I/O types, all except for the digital outputs, the analog output can be configured on the fly in the field using variables or registers. So again, it's just like the universal analog input, it's just like the flexible input. If you want to configure those in the field from a screen that you develop, no problem. That pretty much covers the material that I wanted to share with you today. I think hopefully you've seen that those inputs and outputs that are built into the base, those 6 I/O points, are pretty flexible and they add a lot of value in a lot of applications. So whether you just need to add a little bit of I/O like that to your application, or you need to add a whole base full of I/O with additional modules, or even multiple bases, I think you'll see that OCS I/O is pretty darn flexible. Now let's mention the fact that we're here every Tuesday, whether we're fully live like today, or whether we are streaming live a pre-recorded video. Now today, for those who are watching live, you've had the ability to type in to the chat section and to give us questions and comments, and we've had people standing by monitoring that. And for those of you, like a lot of folks do, who are watching on replay instead, you still have that capability. You just do it in the comment section. And we love to see your comments and your questions, and we typically get to those pretty quickly. Now let's talk about next week. What are we covering next week? Well, next week we're going to be talking about scheduling FTP transfers to and from a Horner OCS. So that should be a pretty useful topic for those of you who maybe are doing production monitoring or data logging using your OCS, and you'd like to be able to grab those files at the end of the shift, or maybe you want to send an updated recipe file to the OCS. FTP is really the best electronic way to transfer those files, whether you're grabbing them from the OCS or sending them to the OCS. Okay, so for those of you in the States, I want to wish you a happy Thanksgiving this week. I hope you have a chance to spend time with your family and to eat lots of food. I can guarantee you I probably will be doing just that. Okay, so until I see you next week, let's all get out there and do us some good.